There is an assumption built into almost every new agent architecture today. A perfect memory is the ultimate goal. Store every fact, never lose a single trace, and the mathematical outcome is a system that can only get smarter over time. But empirical evidence reveals a paradox. An agent with perfect recall will often score worse on standard benchmarks than an agent that forgets on purpose. Keep the context window length exactly the same, but add more retrieved documents into it, and accuracy can drop by as much as 20%. The answer can be sitting right there in the prompt, and the agent will still fail to extract it. Intentional forgetting is the mandatory architectural fix for scaling long-context AI systems. Unchecked memory aggregation actively degrades intelligence. Fixing it requires developers to shift their entire focus from how data is stored to how strictly it is curated. I'm the bearded AI guy, and on this channel, I break down the architecture detailed in the book AI Agents in Action. Today, we are focusing exclusively on the hardest half of the memory equation, not what you write down, but what you surface. This happens at the serving layer. Under a frozen model that cannot be dynamically retrained, a massive database only pays off when the system can evaluate and rank those stored facts against the immediate situation presented in a prompt. Look at the landscape of production documentation, and you will see a massive structural bias. Standard search techniques like hybrid retrieval and metadata filtering are highly tooled, highly visible, and perfectly measurable. Forgetting is largely ignored. This bias persists because public benchmarks historically reward recall but underpenalize stale or contradictory memories, making deletion feel like a high-risk operation that might remove the one fact that matters later. But retrieval in production follows a strict operational pattern: rank, then pack. Generate candidate memories, score them against the current prompt, and stuff the winners into a fixed token budget before injection. Because that budget is fixed, the most effective memory stacks actively discard the vast majority of retrieved data, keeping it far away from the active surface. An agent's coherence is not determined by the sheer size of its vector database. It is determined by the ruthlessness of its serving layer curation. If curation is the goal, standard nearest neighbor vector search is entirely inadequate for evaluating complex memories. It only measures semantic similarity, which treats a stale fact from 3 years ago the same as a critical update from yesterday. To fix this, we look to the foundational 3-signal ranking function established by Park and colleagues in the Generative Agents paper. It evaluates every memory across 3 distinct metrics to produce a final ranking score. The first signal is relevance. This is your traditional cosine similarity, a mathematical measurement of how closely the memory embedding matches the user's current query. The second is importance. This is an LLM-assigned poignance score, from 1 to 10, permanently written to the metadata at the exact moment the memory is created. The third is recency. This applies an exponential decay curve based entirely on the hours since that specific memory was last accessed. These 3 orthogonal signals are then min-max scaled and summed with equal weights. Retrieval relies on all of them at once. By forcing the system to evaluate multiple distinct signals simultaneously, you prevent a single factor, like recency bias or a highly emotional keyword, from hijacking the agent's limited context window. Scaling this ranking logic to millions of memories requires splitting the retrieval pipeline into 2 stages: cheap, broad candidate generation, followed by expensive, precise re-ranking. Think of a research library. You deploy a librarian to pull every book that might be relevant, fast, cheap, and generous. Then an editor strictly edits it down to the exact paragraphs worth printing. In production, Stage 1 candidate generation relies on efficient signals. Pinecone, for example, combines dense and sparse signals to cast a wide net across the entire database. Stage 2 applies heavy computation only to the top hits. Vespa uses a second-phase re-ranker driven by models like XGBoost, while systems like GraphRAG expand entities and walk local community graphs. But there is a structural vulnerability here. The most powerful, computationally expensive re-ranker in the world is useless if your first-stage generation fails to retrieve the correct evidence in the first place. You narrow first, then spend the heavy compute only on the survivors.
It is the only architectural pattern that protects the agent's strict token budget during complex tasks. Isolating broad search from rigorous ranking allows the underlying memory store to scale infinitely, without destroying prompt efficiency or driving up system latency. Which brings us to what actually happens to the data that doesn't make the cut. The word forgetting misleads people. It implies the physical erasure of data from a hard drive. Active forgetting relies on 4 precise operations. The first is demote. You lower an item's rank into cold storage. It is removed from active use, but preserved perfectly for audit trails and compliance rules. The second operator is invalidate. When facts update or user preferences change, you flag the existing memory as superseded. The third is consolidate. You aggregate multiple low-level memory traces and distill them into a single high-level summary node, freeing up space while keeping the learned concept. The fourth and rarest is delete. This is the physical, permanent removal of a database entry, utilized almost exclusively to satisfy privacy mandates or strict internal policies. Engineering these policies is fragile work. Take the MemoryBank Python bug. The code meant to apply a decay curve to memories over time, but a simple math precedence error inverted the formula. Stronger memories resulted in a smaller retention score. One misplaced bracket and reinforced memories decayed faster. Forgetting is a suite of sophisticated curation protocols. When executed correctly, agents remain legally compliant while keeping their active reasoning highly agile. We have exact empirical benchmarks proving why these constrained budgets and active forgetting policies are mathematically non-optional. This chart shows how answer quality responds to increased document volume within a constrained space. Levy and colleagues held total context length constant, but packed in more documents. The result is an inverted U-curve, where accuracy peaks and then quality drops sharply by up to 20%. Dew and colleagues found similar degradation as input context length grows. Depending on the model, performance drops ranged from 13.9% all the way to a catastrophic 85%. We see this in active agent platforms as well. Memora tracks an agent's memory score deteriorating significantly over time without active curation, falling from 40.42 in weekly settings down to 19.9 over a quarter. The mechanical cause of these failures is the accumulation of hard negatives. Extraneous, irrelevant documents crowd the extended context window and actively confuse the LLM's attention mechanism. It gets distracted by the noise. Unbounded storage, lacking an aggressive forgetting policy, mathematically guarantees eventual system failure by amplifying that noise over time.
Resolving the tension between keeping deep audit trails and maintaining tight context windows comes down to one core architectural rule. Developers must completely decouple data storage from data surfacing. First, maintain the archive, the vast outer ring where all historical records and audit logs are kept safely intact. Then build the serving indexed, the inner ring, a highly curated surface layer containing exclusively facts promoted into the active prompt. You do not want to naively delete the archive. Research proves that historical timelines are sometimes strictly required for complex reasoning tasks. Erase a superseded fact, and you might break an answer that depended on understanding that timeline. Developing a production agent today now requires perfecting the precise, narrow subset of facts that get promoted to the active surface. AI memory quality is defined by serving layer curation, where ranking takes precedence over raw storage capacity. Look at your own pipelines and ask the hard question: what stale data should your system aggressively demote rather than delete entirely? Drop a comment below with your answers. All of the ranking and retrieval layers we've mapped out today trace back to the foundational work in AI agents in action. It's where the engineering depth for these concepts actually lives. We started with a misconception that an agent's memory must be flawless and limitless. The evidence proves that perfect recall is a trap that degrades long-term performance and clogs the attention mechanism. Mastering intentional forgetting is the final, essential step to building scalable, production-grade AI agents capable of long-term coherence. I'll see you in the next breakdown.